Just in case. Our technical program for today involves the presentation of 5 articles, and this is the session in Aeronautics and Aerospace Engineering. And it's a pleasure to present the first paper of this session, entitled CNN-based DPU for radio frequency signal classification in rescue analysis, in rescue applications. It's presented by Carlos Osorio Cuero and Jose Carranza.
Okay, good morning. Are you listening? Okay, thank you for the invitation. Topic today, evaluation of the DPU acceleration as a convolution neural network for emerging LFE signal classification and future request system. Okay. Continuing today, this presentation, we propose an overview of state-of-the-art LFE signal monitor technologies for disaster response, exploring the hardware performance, signal types typical on the disaster trick areas, our proposed solution, experimental set2 results, and future UAV integration, conclusion, and opening discussion. Okay. In disaster after areas, it is still possible to detect the various electromagnetic signals shown us on the cellular transmission, more color, radio broadcast, and satellite communication. This infrastructure damage or power failures. By using the trilateration techniques requesting, I can geolocation the trapping survivors. The time window for the signal detection depends on the device battery life, ranging normally from the 1 hour 2 hours, many cases, okay? Deployment UAV during the critical 3 hours after a disaster enable a rapid detection of the LFE signals and the creation of the LFE heat map helping to respond to appearing research zones. Okay. The 4B are based on the research and request SAR mission. Several key factors must be considered in the sensor fusion for the wide area coverage, cooperation of B, operation to increase detection probability.
Could you please put the complete screen for the slide?
Sorry, you can see the slides.
But we can see it bigger. So will you put, please, Control L or something like that?
Okay. Now? You see or no?
Nothing.
Okay. Okay, continue the presentation. Okay, the topic, the overview.
Put the microphone on.
Well, one moment. Yeah, perfect. Sorry. Okay. Well.
Hit Control L. I think.
It's perfect. Okay, now. You see the best presentation or?
Now we see it.
Okay, perfect. No worry. In reference to the state of the art, it's normal you can see the current research on the operation of the system, action the propagation for the laboratory implementations to the real world disaster scenarios. And normally, a 3-minute sensor domain, they are typical using, and normally is the identify using different spectral visual, detection, the light detection, signal, the vital signal, or a spectrum monitor RFC, okay, to detection the activity transmitter, okay. A normal spectrum monitor, this board focus on the RF screw monitor with selection on the LTSR, normally customizer or commercial hardware, are the primary hardware performance due to the low cost when performance adaptive importance. Okay, I can integration different elements. For example, performance techniques, adapter array antennas, and low noise amplifiers. This hardware improves on the response of the hardware. Okay, next, capture the data enable real-time and scene identification, spectrum survivor, RF sign generation, and geolocalization, RF sort. Okay. Identification, the signal is important, but the more probable transmission during disaster, we define the signal typical to buy other training data sets, delimiting the training, and focus on the cellular service, broadcast radio, node call, and satellite phone. Okay, this is the two on the limitation on the hardware. Okay, the selection, the main consideration, the carry power and the propagation distance. Okay, this information and the validation in laboratory. Okay, now next steps for identification hardware. It's important the FIA architectures, the shows the FIA basic architecture offered important low latency because the application on the things to real time. High reconfiguration is case to selection different strategies de deep learning for detection the different signal. Low power consumption important for adapter in the UAV has a limitation in the light battery. Compactor of the floor switch for UAV important reduction of the emission and the size. Okay. Data flow architecture connector the PC to FIA and deployment GPU acceleration for the linear interface. This deployment is improved in acceleration. Okay, normally in the compiler in Linux, and create one imagine for running into the FPGA. Okay. Now, machine learning solutions is important in this world. Identification three basic neural network model. Okay. Evaluation, what is the improve in this case, focus on the reduction, the low attention, consideration on the different in performance. Okay, the performance the model into the hardware. Okay, in this case, very simple. One of the CCNA basic. Next, other models, BEA, ResNet. ResNet is improve of the network, in focus of the working condition, the high noise. Okay, because in this scenario, the request disaster area, no communication present on the high noise and fading and the problem. Okay. If this is models things to the configuration in the area. Okay. In the model, normal convolution, the ReLU, basic model for running in FPGA. Okay. What is the limitation in the hardware in terms of the DPU or the memory? Okay. Different network. Okay, this is the show. Okay, next text. This is a solution. Focus us on the compression. Okay, because I need reduction on the time of the processing important because I need limitation in the battery. Okay, the UAV. Okay, in this case, the model we compare the terms and accuracy and robustness. Apply the different strategies bus one on the quantification and putting the neural network. Okay, in this case, it's a processing in the using the PC on the servers and compilation this model and the compilation of the program in the FPGA. Okay. Parameter the quantization techniques, you can see the improves in terms of the parameter accuracy. Okay, normally is entry off entre when you apply this technique, entry off between the accuracy and the reduction the size model. Okay, in this case, in focus of the accuracy around the 19%. Okay, so it's good. Will never occurrence. Okay, and then in this place, apply the quantization techniques, reduction de 32B a 8 bit. Okay. As in the field text, I can see on the proposed on highlights the post-training quantization. We can see the problems in the field quantization because limitation in the recurse of the FPGA. Okay. One application the quantization, we can apply the ResNet. Okay, ResNet is improve the network is okay. Normally, we apply in the evaluation the network quantification. The P utilization the 75 or 18%. You say the time cruiser. Okay. In this case, you can see the problems because the limitation in the internal recursion or the problems in the running this model on the in FPGA. Okay. Now test the quantification application. The post quantification improves the node robustness. It's important because this system and the working in the disaster and high incrementals robust their robustness, reducing the decision to survive fragility. Important, in critical the future impacts and low input dynamic range distortion. This is the problem is I can limit the hardware. Okay. For experimental sector, it's important what is the final strategy for the testing because in this moment, I had identification different elements, the field element and the hardware, LTCI commerce, and the backend monitor, and the program, the PU FPI, and the front-end monitoring. Okay, the front-end monitoring, the user in configuration this in different model, the program on or and selection the different expectation of the neural network. Okay. The monitor is running in real time. Okay, for the user defines the testing and the start, and they send the communication PC or to FPGA, and reading the capture the scanning frequency and testing convolution and the showing the different network, different power the capturing the area. Okay. In the experimental sector, initial static test, near field condition, where is simulation, is in this case, USP and Doppler effect, where no consideration distress. Okay, so normally defines what is the area or distance the far or near far of the boundary important depending on the different type modulation. Okay. Next parent, we con classification, occurrence, evaluation of different case, the quantification or no quantification, and what is the range occurrence, depend of the noise important. Okay. The next experiment is this experiment, the outdoor test, important, the field testing involved, capture the layer field signal, detection and classification in the real time, geotapping detection, the point for the heat map visualization. Okay. In this case, capture the level power important for the frequency. Okay. in the test, the outdoor on the marking with the point, the testing, and identification what is the peak, the power, okay? Aquí se está the modulation, okay? Esto outside, of the condition, the noise, and interference, okay? Right. Okay, this is the testing, different scenario on the outside, on the precision, on the indoor, okay? For the checking what is the noise interference, okay, validation what is the possible or the signal test identification. The future identification in that moment, validate the real-time performance in that moment, in these moments, and the evaluation the hardware, okay? Identification what is the limitation, the hardware and the FPGA, okay? Next year, integration the hardware into the UAV and testing the simulation disaster scenario, okay? A simulation the high level noise and interfering. What evaluation the performance, okay? What performance is the network in similar disaster scenario, okay? Integration the sensor function, the visual, the integration the sensor of the camera, microphone or other for detection the victim disaster, okay? Now in conclusion, the pre acceleration, the design a successful deployment and the RFSO performance. The proposed modification transmission model end-to-end. The move I need the downstream heuristic, important. Current role the NATC is in laboratory, okay? I need the validation is occurring in scenario simulation, okay? Important. Demonstration potential at the swipe contraction, the reduction the size, dimension, and the save the power. Focus on the UV performance in media communication and the required operation. Okay. So any question?
Thank you very much for the presentation.
Okay.
Are there any questions? No, seems there are no questions.
Okay.
Thank you very much.
Okay, thank you. See you.
We have 2-3 minutes.
Hello? The microphone is in off. Can you hear me?
Can you hear us? Hello,
Hello?
what are you doing?
Yeah, I'm here.
Turn on the camera and put your slide on the screen.
My camera is broken. I'm sorry. I will share my presentation now. Can you see the presentation?
Okay.
Okay.
Okay.
Okay.
How about your camera?
My camera has broken. I'm sorry.
It's because of demands of the IEEE that requires that every author shows his face, but it's okay.
I'm so sorry.
Our next paper is called Decoding Ship Signatures in SAR Imagery. using deep learning for maritime surveillance.
Yes.
The presenter is Ms. Iram Bayraktar
Yes.
from the Unmanned Intelligence Systems Lab in, I believe, in India.
Yes.
Thank you. You have 20 minutes for your presentation, and you can start
Okay.
at 12:20.
Hello, everyone. My name is İrem Bayraktar. I am a research assistant in Unmanned Intelligence Systems Laboratory. I am from Turkey. Today, I am going to present with title Decoding Ship Signatures in SAR Imagery using Deep Learning for Maritime Surveillance. This is a brief outline. As we all know, the oceans cover more than 70% of our planet, and they are incredibly dynamic environments. And monitoring what happens on the sea, like ships, is not only about the logistics and trade, it's also about safety, security, and protection. So the timely discovery of ships can literally change the course of critical events. And however, doing this in practice is quite challenging. And weather conditions are unpredictable. Lighting changes, also some traditional optical sensor struggles because of cloud and darkness. In this term, there is SAR images, synthetic aperture radar. We say synthetic aperture radar, SAR image, and SAR works differently from optical cameras. So there is also a lot of challenges in SAR imagery. In this study, we set out to compare two leading deep learning algorithms for ship detection in SAR imagery, faster RCNN and single-shot multi-box detector. And our main goal was to understand how these two models works, and one focused on the precision and the other algorithm focuses speed. And we wanted to see which algorithm has better than the other algorithm, and we trained both models on the same data set and under identical conditions to ensure a fair comparison, and then we analyzed their results from both qualitative and quantitative perspectives. Let's talk about object detection background. It's also much more page. Object detection algorithms divided in two terms: two-stage object detection algorithms in here and single-stage object detection algorithms. In two-stage object detection algorithms detect the object in two times. First, algorithms comes region extraction, feature extraction, then come first input. In the second time, algorithm detect its classification. In single stage object detection algorithms such as SSD algorithms, the algorithms detect the objects and classify these objects in one time. Let's talk about faster. Let's start with faster CNN algorithm. Is one of the most accurate detection frameworks available. It's a two-stage object detection algorithms, and first in here, faster CNN proposes potential regions in the image, and that might contain objects using a region proposal networks (RPN) we say. Then it classifies each proposed regions and refines its bounding boxes. And the benefits of the to process precision is high accuracy, and especially for small and or partially visible objects. And however, because of its complex architecture, faster CNN tends to be slower at inference time. And you can also think it's a careful observer. Let's continue with SSD algorithms. SSD algorithms is a single shot detection algorithm. One of it performs both localization and classification in a single forward pass through the network, and this design makes this much faster, enabling near real-time detection in real-time detection operations. And SSD uses multi-scale feature maps, meaning we can say it looks at an image at several resolution, and this helps it to detect both small and large ships in one shot. And in our implementation, we also included multi-head attention layers it to refine the model's focus and improve its ability to distinguish ships from the background clutter. We can say, in short, SSD sacrifices a bit of accuracy to gain significant speed, and it making ideal for the real-time object detection operations. Let's look at some data set overview. We created a custom SAR dataset. It's included around 3,000 image of ships. It is captured under different maritime conditions. And to make sure the models learns robustly, we applied some data augmentation, such as rotation, flipping, scaling, some of constraint and lightning conditions adjustments. And this step was especially important because the real world scenarios, ships come in all shapes and orientation, and environment conditions vary widely. And by expanding the data set through augmentation, we help the models with the generalized better and perform more consistently. And after that, we created data set, and we divided into 3: training data set, validation data set, and test data set. Around 75% of data set is training data set, 10% validation, and 15% for testing data set. And here you can see two visual analyses for our annotations. On the left side, the scatter plot shows bounding box with versus heights, and it's revealing that ship sizes, ship sizes vary dramatically from the small boats to large cargo vessels. And you can see figure 4 on the right side. The aspect ratio distribution shows a wide range from very narrow ships to compact ones. And this diversity in object shapes and size, it makes task particularly challenging. It's also realistic. If we continue with training setup to maintain consistency, both models were trained on some computational environments. You can see that GPU, these models we used. Let's continue with the test results. You can see in this figure, you can see ship detection from the both models, FSR, CNN, and SSD. The top row shows the results from the SSD, and the bottom row comes from the FSR CNN detection results. Please notice that how faster CNN detects more ships, including much more smaller algorithms. You can see much more smaller ships, and SSD still perform well, but in larger ones. We can see that we can already see the trade-off. SSD is fast, but faster RCNN is more accuracy. And also we can look at the numbers across open ocean, coastal and average environments. Faster RCNN algorithm consistently achieved higher precision in every terms. Higher precision, higher recall, higher map, higher F1. But SSD algorithm has much lower in precision, but it's more faster than faster CNN algorithm. In conclusion, to sum up this study, this study provided a comparison of two leading deep learning bodies for ship detection in SAR imagery. Faster CNN delivered higher accuracy and robustness, while SSD provided much faster processing times. Both have their strengths, and if you are building a high-end system for defense or environment monitoring, where accuracy is critical for our study, faster RCNN is the way to go. And if you needed lightweight and real-time detection, then SSD is a strong choice. Thank you for listening to me.
Thank you for your presentation. We would like to see if there is any question. There's one question. Yeah.
Thank you for the presentation. You mentioned about the strategy is robust. What kind of disturbance did you consider, or uncertainties, I don't know, but what kind of disturbance did you consider to say that the strategy is robust?
Can you ask again?
I said that you mentioned that the strategy, that your strategy is robust. The question is, what kind of disturbances did you consider to say that the strategy is robust?
Yeah, in SAR imagery, we changed the optical image from to SAR imagery, and we do object detection. I guess I didn't understand your question clearly.
To interrupt, he's asking, why do you claim that the strategy is robust? What type of disturbances were you considering?
The object detection algorithms, actually, I didn't understand which strategy. We change the optical image to SAR imagery, and we create a data set. Then we do training, then we do test, and it's
Then is the algorithm, well, can the algorithm identify the ships if, I don't know, if there is an obstacle, maybe to maybe in the image there is an obstacle, your algorithm can identify the ships in this
yes,
scenario?
yes. there is some challenges in SAR imagery also. Yes, these are actually not much good algorithms. I mostly works on YOLO algorithms. Yes, but in here their most challenging is small ships, but we can't do much more things in such small ships. But one of my studies, I did some mechanism. I add some mechanism into the algorithms, and we did more accuracy in the detection. But there are a lot of challenging in SAR imagery, and in algorithms we just improve the algorithm, but not much more things.
Thank you.
Okay.
Thank you very much for your presentation. Are there any other questions? No? Okay, thank you.
Thank you. And Dr. Bakırcı, the next presentation. Dr. Bakırcı is my advisor, and yesterday he got a traffic accident. Now he is in hospital, so I will present his presentation. He has
Few minutes.
hello.
Can you please share your screen with us?
Okay. Can you see the screen?
Can you put Control L so that you have a full screen? And how about your camera and your microphone? Are they on?
Yeah, it's on.
All right. Pronounce your last name, Murat Bakirci or Bakirki?
Bakirci.
Okay. And I understand that's not you? Our next paper is presented by Murat Bakirki, and it's called Simulation-Based Real-Time Object Detection and Autonomous Vehicle Tracking in UAVs using YOLOV 13 and Deep Sort with ROS2 framework.
Hello, everyone. Again, it's me, İrem Bayraktar. Dr. Bakırcı is my advisor. He got some injuries, so I will present this presentation, his study. Today, I will talk about the simulation-based real-time object detection and autonomous vehicle tracking in UAVs using YOLOV 13 algorithm and Deep Sort with the ROS2 framework. Here's a quick overview of today's presentation. I will begin with the motivation and introduction of the study, and then I will explain the system design and methodology, including the visual processing line, system functional performance requirements, simulation environment, and experimental design, and also real-time control loop. And after that, I will talk about results and the summary of our findings. In this study, the main goal is to develop fully integrated UAV systems capable of real-time object detection, multi-target tracking, and autonomous flight control in all operating within a simulation-based environment. And to achieve these, we combine deep learning-based visual perception with the real-time robotics framework. More specifically, we used the YOLOV 13 algorithm for object detection, Deep Sort for multi-object tracking, and PID-based control system for autonomous target following. In our system was implemented within the ROS2 framework, and we tested in Gazebo classic simulation environment using the ArboPilot software in the loop setup. In our experiments, the UAV was able to detect and track vehicles such as ambulances, bus, and SUV models in dynamic urban traffic scenes while automatically adjusting its flight according to the visual feedback it received. Let's start with some background. Automation is one of the defining features of modern engineering. In the fields of UAVs, it's a critical role in applications such as surveillance, traffic monitoring, environment observation, and search and rescue operations. To move from semi-autonomous to fully autonomous systems, UAVs needed to integrate three core abilities: its perspection, tracking, and control. Perspection allows the UAVs to understand its environment. Tracking helps it maintain areas of moving objects, and control ensures responses the stable response and stable motion. Recent advances in deep learning, especially with architectures like YOLO algorithm, have made real-time object detection highly accurate and efficient even for small and or fast-moving objects. At the same time, tracking algorithms such as Deep Sort enable the drone to maintain identity consistency for multiple targets, even under collisions or sudden motion. And when combined with a responsive control loop such as PID controller, these technologies enable fully autonomous UAV behavior. Our system architecture consists of three modules: the visual processing pipeline, the car target tracking module, and also the PID-based control mechanism. All of these components operate together within the ROS2 environment, communicating in real time, and also the system was designed to meet strict timing requirements. And for example, object detection must be completed within 30 milliseconds, while total end-to-end processing time and from camera input to control command, it must stay below 120 milliseconds. We also defined performance targets such as the mean average precision map above 0.80 and multiple object tracking accuracy above 0.75. And for testing, we used Gazebo classic simulation environment integrated with RDUPLET SITL. And this setup provides realistic physical dynamics, allowing us to test flight control and perception in synchronized visual conditions. And the UAV module used in this simulation was a quadrotor equipped with a downward-facing RGB camera, and the scene simulated an urban traffic scenario with multiple types of ground vehicles, such as ambulances, buses, and SUVs, moving in different directions and speeds. We also integrated Q ground control, mission planning, and real-time telemetry monitoring. Each test lasted about 10 minutes, and all communication data, such as image processing delays, and control responses, it were recorded and analyzed. Let's talk about the perception part, the visual processing pipeline. In this core, the pipeline uses the YOLO 13 model for object detection, and we retrained this model on a custom dataset, combining public UAV datasets, Wistron, and UAV DET with image it's generated in simulation, and the model focused on three object classes: ambulance, bus, and SUV models. It was trained for 100 epochs at a resolution of 640 by 640 pixels. By the end of training, and we achieved a map 0.5 about around 90%, 91% also, with no signs of overfitting, indicating strong generalizations. And after detection, the data was passed to deep sort, which assigns to unique ID to each object and tracks it also across frames, even during short equalization. And this ensures stable tracking over time. And of course, detecting and tracking are only part of the challenge. The UAV must also react to what it sees and what it's that where the PID-based control system comes in. We compete the offset between the target's position and the centers of the image, and this error value is then fed into a PI controller. It's a simplified form of a PID that uses only proportional and integral components. We also deliberately omitted the derivative term because it tends to amplify noise in visual signals. And also the controller runs at the 50 Hz, generating velocity and yaw commands that are published in ROS2 as twist message. These commands are then sent to a flight controller through a MAV-link protocol, and the setup ensures smooth, responsive adjustments during the tracking. Yes, now let's move on the results part. And our systems achieved an average detection accuracy of 88.4%. And also for tracking the MOTA score, it's reached 70 around 880%. It's again higher than our target. And the ID switch rate was also extremely low, and it's showing that the systems can maintain consistent identifiers for each object. And to the end-to-end latency here was extremely also low, and it's about no, it's not low. It's around 140 milliseconds, and it's also comfortably below the 120 milliseconds requirements. These results prove that the proposed system is both accurate and fast enough for real-time UAV application. Here we examined how the control systems responded over time. When the target's deviation from the image center was large and the controller quickly generated stronger velocity commands, and as the deviation decreased, the control output stabilized. The UAV typically achieved full alignment with the target within around about the 1 to 2 seconds, showing that the PI controller provides a good balance between the responsiveness and stability. Overall, the tracking process was smooth without the oscillation or overshoot. In this figure, you can see 3D flight trajectory of UAVs following a moving vehicle. Here, the red curve represents the vehicle path, and the blue dashed curves. Here, the blue dashed curve shows the drone's tracking path. And as you can see, the UAV system successfully followed the vehicle in a synchronized manner and maintaining a stable distance and direction. And this confirms that our system achieves coordinated and real-time tracking and consistent flight control throughout the entire sequence. And to conclude, this research presents a complete simulation-based UAV automation framework that integrates deep learning, perception, multi-object tracking, and real-time control within a single ROS2 architecture. The system meets or exceeds its target metrics in terms of detection accuracy, tracking stability, latency, and control responsiveness, and the modular structures allows easy adaptation to real-world UAVs, especially on embedded platforms like NVIDIA Jetson or Raspberry Pi, paired with Arduino Pilot. And for future works, we plan to extend this framework with sensor fusion techniques such as GPS and LiDAR integration, and as well as more adaptive control algorithms to make handle real world like wind and lightning variations. Thank you for listening me. Any
Very
questions?
much for your presentation. Are
Thank
there
you.
any questions? I have a question. Can you go back to the slide where you have the PID controller?
Here.
Okay. Yeah. Sorry. I'm wondering if this PID controller is working in open loop because I don't see any feedback in this diagram. Can you explain what's going on? Are you getting some feedback somehow?
Yeah, there is a feedback, but I don't know how because it's my professor's study. I don't work in control systems. I'm just working on object detection object detection algorithms. I said the professor has like accident, so I don't have much information about this study. Just smooth information. But I'm not
Okay,
open.
thank you very much for your presentation.
Thank you.
Okay, next paper is going to be presented by the same person. And the title of the paper is Scale-Aware UAV Detection in Aerial Imagery using a refined YOLO V8 with high resolution feature integration. Can you please share your screen with us? And all right, thank you. You can start right now.
Hello again. Now I will talk about the scale-aware UAV detection in aerial imagery using a refined YOLO 8 algorithm with high resolution feature integration. And now I will begin with some brief talk, then multi-scale feature enhancement and clustering-based analysis of bounding box dimensions. And also in the result part, I will talk about the comparative evaluation against baselines and comparative analysis with newer YOLO architecture. Then I will have some sum up. Uh, in this study, detecting unmanned aerial vehicles, we can say UAV, in aerial imagery has become an increasingly critical task in recent years, and especially for surveillance, border control, and public safety. And however, UAVs often appear as a tiny objects in large images, and they are frequently surrounded by complex backgrounds such as clothes, buildings, or vegetation. And traditional object detectors, including earlier YOLO versions, often missed these small-scale UAVs because they are lose fine spatial details during the downsampling process. And in this study, our goal was to improve small UAV detection accuracy while keeping YOLO 8's real-time speed and efficiency. To achieve that was introduced two main innovations. First, we added a high-resolution feature map to the detection head to better capture fine details. And secondly, we performed a clustering based analysis of bounding box dimensions to make the model more aware of UAV size variation. Let me briefly explain the background. YOLO 8 already introduced several strong features. It's anchor-free, uses a decouple head, and has a compact backbone design. And however, even with these improvements, it still struggles when objects are very small, low contrast, or partially occlude. And to overcome this, we refined the YOLO 8 algorithm architecture. Sorry, YOLO 8 algorithm architecture specifically for UAV detection in aerial imagery, and we added a new high-resolution detection layer with a stride of 4 pixels. This allows the model to preserve low-level texture and edge information, which is extremely valuable when UAVs occupy only a few pixels in the image. In addition, we use k-means clustering analysis of bounding box dimensions across our UAV dataset, and this helped the model learn scale-aware features by adapting the natural size distribution of UAVs. Now let's talk about the first component, multi-scale feature enhancement. In the original YOLO 8 model, detection is performed at 3 scales, typically at strides of 8, 16, 32, and it known as P3, P4, and P5. These correspond to progressively deeper layers in the network. And while deeper layers capture more semantic information, they lose spatial precision, meaning small UAVs can easily disappear. So, in this study, we introduced a fourth detection level. it's called P2 with a stride of 4. These layers focuses on high resolution spatial features, capturing fine grained textures, edges, and contours. You can see in the figure, this figure have 4 scale detection head, P2, P3, P4, and P5. It enables the network to maintain both semantic richness and detailed localizations. We can say, in short, P2 helps the model see the small UAVs that earlier YOLO versions would normally miss. Now, let's move the clustering-based analysis of bounding box dimensions. UAVs come in very different shapes and size, and from tiny quadcopters to large fixed-wing drones. To capture this diversity, we applied K-means clustering on all bounding boxes in the training dataset, and each bounding box was represented as a point based on its width and height in pixels. You can see in the figure, this clustering reveals both the size diversity and distribution imbalance in the dataset, and this approach ensures the model it doesn't favor only large, easily visible UAVs, but also learns to detect the small and subtle ones. And these clustered were then used to guide model training, and they provide realistic data-driven anchor dimensions and help balance the model's sensitivity across different UAV classes. In the figure 3, you can see in this figure we found 8 domain size clusters, which we labeled C1 through to C8, C1, C2, C3, C4, C5, C8, C7, and C6, C7, and C8. Each cluster corresponds to a typical UAV size category in the dataset, from the smallest consumer drones to the large military type UAV systems. Yes, now we can talk about the results. We compared our modified YOLO 8 with the YOLO 5, YOLO 6, YOLO 7, and also the baseline original YOLO 8 using the 5 metrics: precision, recall, F1, map 0.5, and map 0.5 to 0.95. Across all metrics and UAV size classes, our model achieved the best or second best performance in almost every case. And for example, the modified YOLO 8 achieved and map 0.5 in map around 0.95 for the largest UAVs, and it still performed extremely well for the smaller classes. It's a significant improvement over the YOLO 8 and YOLO 7. And its F1 scores range from the 0.71 to 0.96. It's showing that it maintained both high precision and recall, and this means our detector not only finds more UAVs but also makes fewer false detection. And even more importantly, the improvements were most visible in small object classes, confirming that the added high resolution layer truly made a difference. And to further test robustness, we also compared our model against the newer YOLO architectures, YOLO 9, YOLO 10, and YOLO 11. Despite being newer and more complex, our modified YOLO 8 algorithm remained highly competitive often matching or even surpassing them, especially in the small and mid-scale UAV categories. And for instance, in the small UAV class C3, our model achieved a zero point 0.5 map at 0.5 of around 0.8, and it's outperforming YOLO 9 and YOLO 10, and also nearly matching YOLO 11 algorithm. The key takeaway is that our model preserves YOLO 8's efficiency and real-time speed while reaching performance level comparable the state of the art architectures. And in terms of inference time, the modified model runs around uh, 26 milliseconds per image, and which is still real-time capable for this algorithm. Here, in this figure, we can visually compare detection results from the different YOLO versions. You can see that the earliest model from YOLO 5, YOLO 6, YOLO 7, YOLO 8, and we completely uh, missed the UAV's smallest in the image, and you can see modified YOLO 8 along with the YOLO 8, YOLO 10, and YOLO 11 is successfully detects it, and this clearly illustrates that our modifications significantly improved the small object sensitivity of YOLO 8 algorithm. To summarize, this study introduced and refined YOLO 8 architectures that improves scale awareness and small object detection for UAVs in aerial imagery by adding a high resolution detection layer, means P2, and using clustering-based bounding box analysis. We made the model more sensitive to UAVs of all sizes, from tiny drones to large aircrafts, and the model achieved state-of-the-art performance across all major detection metrics while maintaining real-time inference speed. And even compared with newer models like YOLO 9, YOLO 10, and YOLO 11 algorithms, our approach stayed competitive and efficient. And in the future work, we plan to explore like transformers-based attention mechanism and neural architecture search to further enhance detection performance, especially under challenging conditions such as nighttime or adverse weather conditions. Thank you for listening to me.
Thank you very much for
Thank
your
you.
nice presentation. It was kind of short. Are there any questions? No, apparently there's no questions. I thank you for your multiple participation.
Thank
Thank
you.
you very much.
Thank you.
Well, our next and last paper is called Design of a Robust Singularity-Free Controller for the Flight Modes of a Quadrotor Tilt-Wing Convertible Drone. The paper is co-authored by Martin Rios Juarez and Eleazar Sanchez Horta and Octavio Garcia Salazar. It will be presented by. Okay. Thank you very much. And we're going to start in a few seconds.
So, hello everyone, my name is Martin Rios and I come from the Robotics and Advanced Manufacture Department of Cyberstab Saltillo, with collaboration with the Aerospace Engineering Research and Innovation Center, Department of the Universidad Autónoma de Nuevo León in Monterrey. And today I'll present to you my project called Design of a Robust Singularity-Free Controller for the flight modes of a quadrotor tilt-wing convertible drone. And so, first of all, a brief introduction. What is a convertible drone? A convertible drone, or a convertible unmanned aerial vehicle, is a hybrid flying machine that was developed with the intention of combining the features of fixed-wing aircraft and rotary-wing aircraft, with the intention to allow the transition between hover and cruising flight. This can be done by tilting the rotors, like the tail rotor, tilting the wings, like the tail wing, or even tilting the entire aircraft, like the tail seater. In our case, we'll be focusing only on the tail wing. And so the main problem that comes with designing any type of convertible drone comes during the transition phase. In the case of a tail wing, as the wings rotate, the rotors no longer produce total vertical thrust, while the wings still don't generate sufficient lift to keep the aircraft airborne. So if we're not careful enough, we might come to the problem that the drone falls off the sky. And so therefore, developing a control strategy that guarantees smooth and robust transitions while keeping the aircraft stable is essential for reliable operation. Now, for the dynamic model, the aircraft is modeled as a rigid body with 6 degrees of freedom, and the derivation of the dynamics is accomplished through the Newton-Euler formulation. In our case, in the dynamics, we have the quaternion expressed as a transformation matrix, where we have the thrust forces, the forces generated by the wings, and also we have the gravity force, plus a vector that considers model uncertainties and external disturbances on the position dynamics. And on the attitude dynamics, we have the moments that appear on the because of the aerodynamic forces. We have the moments that are generated by the control surfaces of the drone, such as the ailerons, the elevators, and the rudder. And we have the moment generated by the gyroscopic moments of each rotor. And we also have a perturbation vector. Now, these two vectors are unknown, but we assume that are bounded in such a way that we can assure the exponential convergence of the attitude control. And we also have the quaternion kinematics that connects both dynamics between each other. And so the total thrust force, if you can see, it depends on the wing tilt angle. And so when the angle is in pi/2, meaning that we are in vertical flight, the total thrust is going on the z-axis, and when we transition to horizontal flight, the thrust is going in the x-axis. And so for the aerodynamic forces on the wings, you have two main ones, each wing. We have the drag forces and the lift forces that depend on the drag and lift coefficients that depend on the angle of attack. And since these forces are expressed on a wing frame, we transform them using a rotation matrix that transforms them from the wing frame to the body frame. And so for the control, we are using integral sliding mode control. So given a desired angular velocity and a desired quaternion, which I'll define later, the additive errors are defined as this, where in the case of the quaternion error, is the product between quaternions, between the actual quaternion and the conjugate of the desired quaternion. And so to facilitate the control design, we use a parameterization in terms of the nominal reference with the, excuse me, with the extended additive error defined as the actual angular velocity minus the nominal reference, no, the extended error of the angular velocity. And so we can rewrite the additive dynamics in terms of the extended additive error. And so the nominal reference angular velocity is defined as the desired angular velocity minus a scalar gain times the desired quaternion expressed as a transform rotation matrix multiplied by the vectorial part or the imaginary part of the error quaternion plus a vanishing term minus the integral part where the sigma is equals to the integral of the hyperboreal tangent of the sliding surface that is given by the term nu that considers both the errors of angular velocity and the quaternion errors. And the sliding surface is given by that term minus the vanishing term. And so we propose the following law, which is minus KD, which is a diagonal positive definite matrix that multiplies the sliding surface plus the integral size, the integral part, where gamma is also a positive definite diagonal matrix. And so this law ensures the finite time convergence of the sliding surface and its robust model to model uncertainties and disturbances. Now, for the position control, we divide it into two parts, the vertical flight and the horizontal flight, which we will be transitioning later. So assuming that the attitude control compensates for the disturbances in the position dynamics and that the angle is in pi/2, meaning that it's totally vertical, the translational dynamics can be reduced to that term, where the virtual input represents the thrust force in the body frame. Now, following a similar approach to the attitude control design, an extended position error is defined as the velocity minus the nominal reference, which is given by the desired velocity minus constant scalar gain times the position error minus the integral part, where we have the auxiliary dynamics, where the term nu p, which will be important later, is given by the velocity error minus again multiplied by the position error. And so we propose a virtual control law that ensures exponential trajectory tracking in vertical flight. Now, as you know, drone is a non-directed system. So in order to guarantee that the thrust force converges to our virtual control input, the thrust magnitude and direction are defined as the thrust is given by the magnitude of the virtual control input, and the direction is given by the other term, that is the normalized vector of the control input. When we solve that equation, we can get the result of this the design quaternion for vertical flight, and we consider the third term of the scalar part of the vertical part of the quaternion equals to 0, meaning that we disregard the control of the yaw in orientation. And so by using the quaternion kinematics that I show you in the dynamics, we can get also the angular velocity corresponding to that quaternion. And so for horizontal control, the process is very similar. The only thing that changes is the direction of the thrust. Instead of going against the z direction, it's going towards the x-axis. And so we repeat the same process. And by solving the undirected direction problem, we can get also the desired quaternion and the desired angular velocity for horizontal flight. And so during the vertical to horizontal transition, the convertible drone must first build sufficient forward velocity, therefore enable full horizontal control. To achieve this, the control input is temporarily redefined as the velocity error minus only the control in the z-axis, meaning that we retain only the altitude control. This allows the vehicle to accelerate freely without being constrained by the position controller. And so once adequate speed is reached, the full position error is gradually reintroduced to recover complete trajectory tracking. And so here we have a graph where we start by the convertible drone giving us the actual position and velocity. Then using a desired trajectory, we send that into the flight mode interpolation, where we can add or remove the full position control. Then we send that into the position control. We calculate the vertical flight and horizontal flight. We calculate its respective virtual inputs. Then on the rotation solution, we calculate the desired quaternions and desired angular velocity, which are given to the flat mode interpolation. And then we select one of the other. And then we send it to the attitude errors. And then we send to the attitude controls, which in return give us the desired torque. And so for the transition, to ensure a smooth transition between flight modes, we make use of a sigma function with linear interpolations for the wing tip angle, for the term that considers the position errors, and for the angular velocity. And so for the quaternions, since linear interpolation does not maintain constant angular velocity, we make use of spherical linear interpolation, which ensures a smooth rotational transition, where beta is the angle between both quaternions. And so for the results, we added a circular trajectory during horizontal flight. Now, if you can see, we start in vertical flight. Then, if you can see this little overshoot, is because we remove the X error. And so since we move the drone forward and we are not compensated for that error, and overshoot naturally occurs. But then when we go back into horizontal flight, we add the circular trajectory. And in that trajectory, if you can see the zoom out of the error, we can see that we added sinusoidal perturbation, followed by a constant perturbation, followed by a white noise perturbation, which is able to compensate for that. And so for the velocity, you can see where we start moving forward, we accelerate, and then we transition, and then we start doing the trajectory for the following of the trajectory. Then we transition back into horizontal flight, and we land. And so again, we can see the velocity in the transition, where we can see that the system is very sensitive during transition. But when we go back into full position tracking, you can see that the error is still pretty small. And so for the quaternion tracking, you can see that for the quaternion is doing a pretty good job at following the desired trajectory. And in our thrust, you can see that on each transition, we do lose some thrust, but the system is able to recuperate from that. And so for our conclusions, this work demonstrated the modeling and control of a two-way convertible drone, incorporating the aerodynamic effects. An integral sliding mode controller provided robust trajectory and altitude tracking under uncertainties and disturbances. And so altitude was represented with quaternions, avoiding singularities and enabling smooth orientation tracking. And the position control was structured in three phases: vertical flight with full position control, transition with only altitude control, and horizontal flight with, again, full position control. And so overall, the approach offers robustness and precise control, so we can be sensitive to approach changes during the mode transitions, requiring sufficient time for smooth interpolation. And so for future work, we want to achieve experimental validation. Future work will focus on developing a prototype and implementing the proposed control strategy in real time. And so that's pretty much it.
Thank you. Are there any questions?
Yes. What is the control objective of the work?
Of the what?
Control objective
Of the what?
of the work.
The work. We want to focus only on the transition phase between flight modes.
What is the? I think this is the general objective. I mean, the control objective is the tracking control, is the convergence is asymptotically, or
We want to use tracking of certain, well, for the tracking of certain things.
do you have a desired trajectory?
Yes.
Okay. Can you show us the results? The image are very small. The labels can I can't see the labels. What is each line of the first image, the position trajectory?
Right. So the green line is the C axis. The red one is the X axis, and the blue one is the Y axis.
Is X, Y, Z the same vehicle?
Yes.
Okay. Then, do you think that is really robust? You said that use an sliding mode control because it is robust, but your sliding surface is not the signal function. It's not, and the sliding mode control is an a discontinuous control, but you use as the hyperbolic tangents. It is not discontinuous. Is this control really a sliding mode control?
Yes, we're using well, it's kind of based off a PID, but using it's based off a PID, but using sliding surfaces.
A PID for the sliding surface?
What can I say? It's really not that. We're using a so you mean this term, no?
B sub Q is an error.
Yeah.
B minus V desired. And sigma is what, the sliding surface?
No, this is the sliding surface.
Okay.
And this term is the integral sliding surface.
Okay. Okay.
But are you saying that the sliding surface is the derivative of sigma?
No. This is the sliding surface. Okay, just like that. This is the integral part of the sliding surface. We're using to reduce.
No, it's an integral of an error.
Yes.
And the switching is very smooth. It's just the tangential hyperbolic tangent, which is like a high gain controller, but not a switching controller. So it's we shouldn't call it sliding. Maybe we should call it high gain control, saturated control. Okay. Good. Are there any other questions? Or were you answering his question already? Did you already answer? Okay, thank you very much, and thank you for attending the session. This is the end of it. Thank you.